Hello, my name is Abdullah and my partner is wakas. Today we will be talking about edge detection. Usually we can easily identify object in an image where there is only one line drawing. Lines correspond to edges or certain changes in images. More semantic and shape information from images can be encoded into edges. It is more complicated presentation than original image. So it can be very useful to extract edges from images to use it for recognition. The ideal result is a drawing line of an artist, but an artist uses object level knowledge. And in an image processing we really can use object level knowledge. Now we will consider only basic algorithm without machine learning, and I will mention how the machine learning algorithm can be constructed for edge detection.
All can see the edges as points of rapid changes in image intensity. Such points can be identified by considering first derivative of the image intensity. Edges will correspond to local extrema of derivative on the slide. I'll give a one-dimensional example from one row in image. Since image is a two-dimensional function, we need to calculate image gradient as a vector of partial derivative of image intensity function. The edge strength is given by gradient magnitude. Because images are discrete, we could approximate partial derivative of optical image. This finite difference in discrete images. Finite difference can be easily written as a simple convolution. Other approximation of derivative filters exist. I put here a robot separator, private, Sobel and Schur operators. These operators both smoothens and estimate finite differences in image. They produce visually similar results. Here are the example of edge maps computed by convolution with these filters. You can see the difference between filters is mostly small.
Consider a single row or column in the real image. Usually the image contains noise. The plotting intensity as function of position, finite different filters correspond strongly to noise. Noise results in pixels that look very different from neighborhoods. So finite differences use a lot of false response. Generally, the larger the noise, the stronger the response, and the larger the number of strong responses. So if the image contains noise, then the real edge can disappear. Let's demonstrate in this slide. The solution is to apply Gaussian smooth first to reduce the noise. After smoothen edges detection kernel identify the edges in our images. Because convolution in associative operation, we can combine both smooth and edge differentiation kernels into one filter kernel. This saves us one operation and produce the same result as applying smoothen and differentiation operator successfully. Here are visualization for derivative for Gaussian filters which can be used for gradient estimation in real images. I give visualization of two filters. One estimate gradients in x direction and one estimate gradient in y direction. Smooth derivative remove noise but blur edges in images. The larger the Gaussian filters, the stronger the smoothen. As a result, we find images in different scales and appliances smoothen with different filter kernels. In this example, if we use small filters, we get a lot of small edges and small details. When we use larger filters with the gradient only corresponding to the large object in the image.
Gradient magnitude estimation is not a complete edge detector. Edges are usually 6 stripes or edges of large image gradients. As you can see in this example, also they receive only if the joint set of points is large gradients without connectivity information that link neighboring points into real edges. These problems were addressed by well-known Kenny edge detector. This is probably the most openly used edge detection algorithm, and we also use Kenny edge detector in our project. It has 2 steps gradient estimation. First, there is non-maximum suppression during that step. The thin multi-pixel of white reaches down to a single pixel width. Second is linking edge pixels together to form continuous boundaries. Here is the example. We take an original image and apply gradient estimation first. The obtained map of gradient norm, you can notice a lot of thicker ridges at the edges. Now, we apply non-maximum suppression. This can be done in several ways. The easiest is just to lose the pixel that are local maxima in the square neighborhood. For example, 3 by 3 pixel. The more complicated way is to identify the points in either pixel row along the image gradient vector. We should interpolate for neighborhood pixel to get these values. So we found a local maximum along the edges gradient vector.
When linking edge points, we use threshes. Threshes is just 2 thresholds. We use high threshold to start edge curves and low thresholds to continue them. This allows us to trace weak edges. If they are connected to the strong edges, weak edges themselves won't be detected. This traces thresholds. Here is the example of thinning on non-maximum separation applies to the edge maps obtained for this particular image. High traces allow us to achieve a balance between an amount of detective edges and noise. If only one threshold is used, we either miss thick edges, which are extensions of strong edges, or get a lot of noise from weak edges alone. By varying the sigma in gradient computation or the size of Gaussian smoothen or the size of derivative for Gaussian filters, it can detect edges on different scales. Or large sigma detects large scale edges. Small sigma detects fine features in images. In this example, you can see that by increasing the size of sigma from 1 to 2, it removes all vertical lines originated from stripes on the rows.
There's a lot of uses of edge detection in the real world. For example, for satellite, it can be used to use edge detection to map out the map clearly. It can be used in robotics and automation. The robots and the auto cars are using edge detection to clearly map out if there's a car is coming or not. Fingerprint use edge detection. License plate, for example, the camera on the road use edge detection to catch the car who is violating the laws. We did our project on edge detection. We use Kenny edge detection. I'll show you a picture of a Canton tower. Let me show you. Wait. So here is a image of a Canton tower, and this is the picture of edge detection. You can see all the noise reduction is used in the Kenny edge detection. So it's clearly mapped out. This is the end of our project. Thank you for watching.